So, hello everyone. I'm happy to be here, and this is my first talk at HEXACON, and today I'm going to speak about some video games research. This is the agenda. First, I will introduce some video game concepts, and next I will present you some very old bug on very old game, and then I will speak about Neverinternight and the multiplayer attack surface. And then I will detail some vulnerabilities, and finally I will explain how to exploit these vulnerabilities to get arbitrary code execution. I will introduce myself briefly. My name is Thomas Dubier. I am a reverse engineer at Synactive. I have been working in the cybersecurity field for 5 years, and in my free time I'll search for vulnerabilities in all video games. On the left, this is my collection of all video games. So I didn't know what to do with them, so I decided to reverse it. Many of these games run on Windows XP, but some of them are re-released to support modern operating systems like Windows or even Android. Publishers often add the possibility of playing online or not just in a local area network. It's also a good target to train your reversing and exploit skills. We often find custom protocols or custom file formats. And I only look for bugs that can lead to arbitrary code execution, so I wouldn't talk about cheating techniques. Let me introduce briefly concepts about video games. Basically, video games is just a loop. A program will process user input, but it doesn't wait for it. And next, it will update game objects like a car type position, or AE state. And at the end, it renders all objects at the screen. Video games are often built with a game engine. Game engine will introduce a rendering engine, physics engine to detect collision, audio engine, scripting engine to facilitate development. And they are also in charge of loading assets. Assets are, for example, texture or 3D models. And game engine often implements overlay on basic features of operating systems to deal with performance. Obviously, networking is the most exposed attack surface. Sometimes we can reach other components, for example, if games allow to update assets remotely. And now I will present some classical bugs and where I found it in very old video games. Here is a first example. It's a straightforward stack buffer overflow in games named Gate of Throw. It's probably due to a typo because the buffer is 800 byte length and the allowed receive length is 8000 byte length. It's very simple to exploit it on Windows XP because we don't have any mitigation. There is a bug pattern that is often found in game using directly. In the good old days, it's common to use an unsecure function like sprintf. And in the matchmaking room, the game displays the games available on the same local network. And they use a format string to display the game name and the player count over the maximum player count. And the reception is a buffer, and the reception buffer is a fixed size buffer in stack. Games doesn't check the announcement game's name, and which again leads to a classic stack buffer overflow. It is the case in Age of Empires Windows XP edition, but not in the Steam version. But we also found these bugs in a game named Disciple Sacred Lands, which use the same format string. Sometimes games implement a hidden feature. For example, Submarine Titans will automatically synchronize a map file between the client and the server. And there is again a stack buffer of vulnerability and the map name. Now, a few words about a re-released game. They often have the same bug as the original version. Some bugs become inexploitable because games are compiled with additional mitigation, but it depends on the date of the re-released. For example, the Baldur's Gate series have been re-released, but they doesn't have address place route randomization enabled. So this is there is an index out of bound bug. Permissions of player are processed like an array of bool, and the admin will send a network packet with index and value that are not checked, which is to an out of bound write in the heap, and it's enough to get arbitrary code execution. To sum up, bugs are a little more hidden over time. They persist during re-released version, and we often find the same bugs where the game comes from the same publisher because they are built with the same game engine. So all these games have bugs that will lead to arbitrary code execution. Most games that are re-released lacks of mitigation. That's why all bugs remain exploitable. For example, American Conquest and Cossacks 2 are provided only in 42 bits. And Windows 10 enforces DIPS, data execution prevention, only when running 64 bits executable. So we have a read-write executable stack on this game. There is another example, which is Alien vs. Predator. Game has been patched by the player community to support a new multiplayer server, but the game loader disables DIP explicitly. And the last example is Diablo 1, which is available on the GOG platform. And the main binary has ASLR enabled, but DLL ships with the game doesn't have. So now let's move on to Neverinternight game. Neverinternight is a RPG game developed by BioWare in 2002. It has been re-edited by Beamdog in 2018, and it will run on Windows, Linux, and macOS natively. It's based on a game engine named Aura Engine, and it can be played in multiplayer online or on LAN. At the beginning of my research, I started by looking for anything that could help me for reverse engineering. It turns out that only the Linux version has debug samples, which is very useful. There is a modding community developing an open source clone of the game engine, but they didn't implement multiplayer functionality. There is one publication about the protocol used in the matchmaking room, which can be interesting. There is also useful tools that already exist to decode assets like character file or save the game on the modules. And there is a license file that help us to check for outdated open source components. There is, for example, a JSON parser, but it is up to date and doesn't contain no vulnerabilities. We can also get classical information about mitigation. We have a standard mitigation enabled like stack cookie, DIP, and ASLR. ASLR are also enabled for DLLs that are installed with the game. So now let's dig into the multiplayer attack surface. We can study how works the matchmaking room. This surface can only be reached via local network. Another protocol is used with a master server doing online matchmaking. In local area network, it's a simple UDP-based protocol where messages are identified by 4 magic bytes, and the game client will send a broadcast message, and the server that are listened on the local network will will answer with information like server name, number of connected clients. After, when a client tries to connect to the server, they will establish an encrypted communication and the client will send the public part of their CD key and the password if it's needed. In the original version, the packets were not encrypted, but in the new version, the publisher added an encryption layer based on libhydrogen, and libhydrogen provides a simple key exchange API based on the noise protocol framework. It's based on elliptic curve and Gimli permutation. Some cryptographic keys are derived from CD key. They can identify the player with that. The network stack is divided in 3 layers. The first layer will decipher the packets. The second layer will handle compressed and fragmented data. And the third layer will decode a game message. Let's get into the detail of the first layer. The protocol is built on top of UDP again. Latency is important in multiplayer video games. That is the reason why many games use UDP with a custom protocol. They can mark some packets as reliable and some others as unreliable. And in this game, packets have one byte header, which indicates whether that packet is encrypted or not. And it's followed by 4 bytes that correspond to the recipient IDs. And the recipient IDs is generating during the key exchange. Once deciphered, data is considered as a frame. We found a header of 12 byte length on the CRC to verify the integrity of all data, either include. There is 3 frame types which are defined in the flag fields. Data frame that contains game message, acknowledged frame that doesn't contain data, and the non-acknowledged frame that are here to signal an error. And there is a flags field which indicate if data is compressed. Once frame is reassembled or uncompressed, client or server will process the first byte of the data to determine the type on the direction of the message. There are server to player and player to server message, and they are encoded in the same way. There are sysadmin messages that are just simple textual commands. Here is an example of a message to eject a player. It's not the biggest attack surface. The most interesting surface are game-related messages, which can update a creature appearance, start a progress bar, add a quest in a journal, and there is approximately 250 message tips. They are formatted as following. There is a major code that indicates the category of message. If it concerns a journal, by example, there is a minor code which identifies precisely the message, and it's followed by a length field, which represents the length of byte stream that can contain additional parameters, like title of a quest, character characteristics, or other. The rest of bytes that is not included in the byte stream contains additional parameters that doesn't need to be encoded in less than 1 byte. To facilitate decoding of message, developer has written a class named CNWMessage. For example, the readInt method ensures that there are 4 bytes in the byte stream before reading a 32-bit integer. There is other methods like readBall, which will read in the bits buffer. Which brings me to the next point, the vulnerabilities. Firstly, we will find the same vulnerabilities that exist in Windows XP version. In this piece of code, client will read an array of integer representing a class associated with class level for a character. Arrays have a fixed size of 8, but the array size is read from the message, and the size is not checked, and it is encoded in 1 byte. This leads to a stack buffer overflow, but today it's not exploitable without a cookie leak. On the further code, this message is sent by the server when the player creates a character that has the same name of already created character. This will trigger a pop-up which displays the class and the class level of each character. And the player must choose between the character saved and the character he has just created. The second bug is more interesting. It occurs when a client processes message about creature parents from the server. Client will read 1 byte as an index without bunch checkings and read 2 bytes as a value. It's an out-of-bound write primitive in the stack, and it's occurring in the loop. We can write up to 10 words, and it's enough to rewrite the return address. But because of ASLR, we need a leak. And the majority of my time in this research was spent to find a leak. It's not an easy task because by design there is free information about the client that the server can query. Fortunately, there is an integer underflow bug when the program initializes the CNW message class. If we send a 2 byte length message, the setRead message method will initialize the decoding class with a length of 0xFFFFF, which is big. If we dig a little bit in function, the message buf member will point to potentially initialized memory. And the length of additional parameters will be initialized with unknown value. And the byte stream and bit buffer will be located outside of memory reserved for the message. And so all we have to do to transform this bug into an out-of-bound read bug is to initialize the byte stream length member. And the first idea is to send 2 messages and see if they use the same memory location, but it's not always the case. Unfortunately, when uncompressed size is lower than a threshold, the program will use a temporary buffer to manage decompression. And this buffer is not erased after use. So we can send the first invalid message to initialize memory. Message will be dropped silently by the client. And we send the second message of 2 bytes, which will trigger the integer underflow bug. The CNW message object will be initialized with a byte stream size greater than the temporary buffer size. And after, we need to find an interesting message handler. For example, if program will read integer in a loop, program will potentially read integer in heap memory. And the most interesting method is the read void PTR method. It can return a pointer to a buffer of arbitrary size if the size comes from the message. There is a few usages of these methods. I found a way to write some heap memory in a file on the client, but I didn't find a way to request this file. So I gave up and I looked for a new surface. There is a scripting engine in this game. It's based on a stack virtual machine with custom opcodes. And looking at the symbol, I saw a way to run arbitrary scripts that are received from the network. But unfortunately, this feature is enabled only in debug mode. But when I looked at this surface, I found an interesting feature. We can send the player to a new server where the player characters will log in. And there is a message handler for that. And we just need to specify an IP on a port, and the client will connect to it automatically. This feature works with debug mode disabled. So when a server sends an activate portal message, the client will request the character file, And the server will send the character file to the client, and the client will save it into a temporary memory buffer. And after, the client connects to the second server and sends the character file. So now let's move to the exploit part. To sum up, we can exploit the integer underflow bugs by abusing this feature. Malicious server will send an activate portal message. After, we trigger the integer underflow bug to send a character file with an incorrect length, and the client will initialize character file with heap memory. And this heap memory will be sent to a second server, also controlled by the attacker. And now we just have to search pattern in heap memory to find the function pointer or the table address. And we get the base address of the program. With this information, we can exploit the first vulnerability to rewrite the return address. When the function returns, the RBX registers point to the current CNW message object. I use the gadget at the top left of this slide. The controlled data is in red on the diagram, and the gadget moves pointers to controlled data into RCX. After, it gets a vtable pointer, and it will call the for function of this vtable. We only control the vtable pointer, so I don't want to play with heap memory. So we are limited to calling only function pointers that already exist in the .text section. And the game includes the Steam library. And during previous research, I found that this library will provide a useful pointer in .text section. There is always a pointer which points to a little function that allows to make an arbitrary jump from RCX, which is very useful because we often found object address in RCX. After that, we just need to make a pivot to our message buffer with some gadgets which end with a call or a jump. And once RSP points to message buffer, we just have to write a wrap chain to do some things like pop calc.exe. It's not time for demonstration. So at the left, this is the victim machine. And at the right, we have two servers which has been instrumented with FIDA scripts. And the victim will connect to the first server. And we will see the console after. With the first server, we will trigger the integer underflow bugs. The client will connect to the second server. And with the second server, we will receive the leak. And we can now exploit the second vulnerability to get an arbitrary code execution. We need the client. We need to play a little bit to have a message, to receive message. So, up. So. We will move to the conclusion. Just wait a little. Okay. So to conclude, modding community provides a great resource for security researcher. We find a very useful tool on debug samples or some sample of code. And the re-released games often lacks of security review. We'll find the same bugs that exist on Windows XP. And in this case, mitigation like Intel control enforcement technology will probably help us to protect against this kind of vulnerability because we rewrite the return address, and Intel control flow enforcement technology provide a shadow stack which simply kills the exploitation if it is enabled with binary. And next, maybe I will research some vulnerabilities in these games. And also another thing that the publisher have fixed these bugs this week. And that's all.